In this problem we have a rotating record that is causing a pure tone to be made. And we're told that the record rotates at 4.32 radians per second, that the frequency it emits is 4.35 kilohertz, and that the length away from the center for the needle is 0.25 meters. So we're asked to find the wavelength of the groove used to cause this. So we're looking for wavelength. So right away, I know we have a frequency, we're looking for wavelength, v equals f lambda. So the velocity of any wave is equal to the frequency times the wavelength. So that's a way to convert between all the time. Now, we know the frequency. We're given the frequency. It's 4.35 kilohertz. We're looking for wavelength, so we just solve for wavelength in this equation. Wavelength equals v over f. So the one thing we're missing now is our velocity. We need to figure out the velocity of this, basically, of our little groove here, how fast it's going along this needle. So that's what this information is given for. We have the omega and our length. So all we have to do is say that our tangential velocity is equal to r omega. So this is from our kinematic equations, our angular kinematic equations. So the tangential velocity at this point is equal to the radius times the angular velocity. We're given both of them so we can figure out our tangential velocity. Actually, instead of figuring that out, what we'll do is we'll just plug v into this lambda equation. So we get lambda equals r omega over f. Now radius is just this length here, 0.25 meters. Omega is given as 4.32 radians per second. Dividing by a frequency of 4.35 kilohertz. Now, we got to make sure when we put this in hertz. Make sure we cancel out that kilo. So 4,350 hertz. 4.35 kilohertz, 4,350 hertz. That's what our wavelength is going to be. We plug all those into our calculator. We get a wavelength of 0.000248 meters, and it's meters because radians isn't a real unit. Hertz is 1 over second, which cancels with this 1 over second here, so the seconds cancel, and we're left with meters. So that meters, so we can write that as wavelength is 2.48 millimeters. There's a zero. No, that's 0.248. So if we move the decimal 3 places, our wavelength is 0.248 millimeters. Or we can also write that in scientific notation as 2.48 times 10 to the minus 1,234 meters. Final answer.